this stage, we have observed the influence of mean stresses, and we even have a simple model that is employed in practice. So let's summarize where we are presently. So we have the following solution approach. Now, if the loading was completely reversed, then I know exactly how the alternating stress for completely reversed loading is associated with number of cycles to failure through the Basque-Couin relation. So this is the relation that we are ultimately targeting. Now, there is, however, a complication, and the complication is that not all loadings have zero mean. Not all of them are completely reversed. So if therefore we are given a loading where there is both a alternating stress and a mean stress that is not equal to zero, one approach is to take these and map them somehow to a equivalent alternating stress. An equivalent alternating stress that is completely reversed such that we can still use the Basque-Couin equation. So if you have a loading where alternating stress is completely reversed, so zero mean stress, then this equation already applies. If not, we try to somehow, based on the values of sigma A and M that we have, we want to calculate a effective, or often called equivalent, completely reversed stress amplitude from which we can predict the life. It is equivalent in the sense that the actual real loading is not completely reversed. It has both an alternating and a mean component that is not equal to zero, but we're just mapping them to find a equivalent completely reversed scenario from which we can predict life. Well, how do we do it? Actually, we've already done it. So what we are doing, for instance, we can use the Morrow equation. Now, the Morrow equation tells us that, well, okay, if sigma A is equal to sigma AR, then you get failure. In other words, you reach a certain number of cycles NF. Well, on the other hand, if you have the mean stress alone, and that's equal to a critical value, in the Morrow case, it is sigma F prime, then you can again get failure with the slightest alternating stress. And now if you have both of them, this is an equality that should be satisfied. That describes the Morrow line. And now what we can do is we can go ahead and solve for sigma AR for given sigma A and sigma M. I don't know what sigma AR is, but sigma A and M have to satisfy this equation, and therefore sigma AR can be solved for, and we can get 1 minus that value, and then I invert it to have sigma AR lying on top, so sigma M over sigma F prime, and then multiply with sigma A. That's the solution of the Morrow relation for sigma AR. So what I'm given is sigma A and sigma M. I'm mapping them to a sigma AR value, right? And then extracting the corresponding number of cycles to failure. So the question is, this is what I have. What is the number of cycles to failure? You go to, for instance, Morrow relation, calculate the equivalent completely reversed value, put that into the Basque-Couin relation equation, and then extract the number of cycles to failure. So this is the general idea that we have essentially constructed graphically and through the equation of a line that we proposed in the last slide. So in general, what you see is really we're seeking some way to map these red quantities to sigma AR. So in other words, we're seeking a function. For instance, this is one function where possibly there are material constants and possibly there aren't, but some function which can take the value of sigma A and M and deliver the corresponding value of sigma AR. I've called that function also sigma AR too, because they are the same thing. Okay, so that's what I'm looking for in general. Okay, if you like, call it sigma AR equals f of sigma A, sigma M. So this is what I'm seeking. And the Morrow equation, and for that matter, the Soderberg relation or the Gerber relation or the modified Goodman relation, they all provide such a function that I can solve for from the equation of a line or of a parabola, etc. So now, since this is one such function, well, there could be perhaps alternatives to such functions, and indeed there are. In other words, this is not the only way. The four possibilities that we have seen, Morrow, Gerber, modified Goodman, and Soderberg relations, they are not the only possibilities. One can propose some other functional relation between alternating and mean stress and the equivalent completely reversed stress amplitude. And it turns out that one such function is called the SWT relation. So let's say here that there are alternatives. Okay, and in doing so, let's just recall that the maximum stress is a function of simply the sum of the alternating and the mean stress components. So among these alternatives, one important relation is the so-called SWT relation, which takes sigma A and M, or conversely sigma max, which is the sum of them, multiplying sigma A, okay, and delivers a equivalent completely reversed stress amplitude. Okay, so this is called the SWT relation. So here SWT stands for Smith, Watson, Topper. And it turns out that this relation is a very useful relation that we should try to remember together with the Morrow relation. So it's a very useful relation, and this is particularly so for aluminum. Aluminum and its alloys. Now, it is, of course, of general applicability, so you can also observe that it might be used for steels as well, but particularly for aluminum is very useful. And one interesting thing here is that, for instance, the Morrow equation, and for that matter, all the other relations that are based on such an equation, they make use of a material parameter, whereas here there is no material parameter. It's just the values of the stress amplitude and the mean stress, boom, you get an equivalent completely reversed stress amplitude value. So there is no material constant. Okay, which is interesting. But still, it works quite well, for instance, for aluminum. Now, one can try to generalize this idea. Okay, so it's a generalization is going to work as follows. What we can do is we can try to change the exponent of max and sigma A. Instead of having 1/2, which corresponds to square root, we can try to put a 1 minus gamma here and a simply gamma there, such that we see if mean stress is equal to 0, sigma max is equal to sigma A, you sum them, you get as a result sigma AR equals sigma A. That's the reason why we have 1 minus gamma there and gamma there. And this is called the Walker equation. Now, the name is not a coincidence. Remember that in fatigue crack growth, we also have seen the name Walker before. So this equation is also of general use. In fact, it is of more general use compared to the SWT relation, because now we can actually capture the SWT relation by choosing gamma equals 1/2, and we end up with that. So this is more general. And gamma now appears actually as a fit parameter. So if you have in the tables or online resources the value of gamma corresponding to a certain material, then it would allow you to perhaps fit or employ and predict a number of cycles to failure for loading with a mean stress with higher accuracy. Notice that no other model that we had so far has a similar fit parameter. Here, sigma f prime is already in the Basque-Kuhn equation. Here, there is no material parameter. This is the only one so far that has actually a material parameter. So having such a parameter is always advantageous when you want to model things. So therefore, we have a general approach where we try to map sigma A and M to sigma AR and go and predict the corresponding fatigue life. And that map might be, say, the Morrow equation, or it could be something different in the form of, let's say, SWT. But one way or the other, these are going to help us predict fatigue life. And let's see with an example how that is going to work.